Okay, let's go ahead and get started. Welcome everyone to GIA Knowledge Sessions. These are a series of talks and seminars about gemology that are fueled by our decades of research. And, at GIA, we rise every morning and we're so privileged and we're so excited to seek and study and learn from gems. And it's our mission to share our discoveries with the world. So I'm really excited to kick things off today. I'm Kelly Giordano, member of the content team here at GIA, and I'm joined by Dr. Mike Breeding, GIA Senior Research Scientist, and he'll be speaking today about something that has a lot of interest in the industry right now, and that's laboratory-grown diamonds and identification methods. So before we get started, there's just a bit of housekeeping. Everyone attending this is automatically muted. If you have a question, please submit it using the Q&A box on the side of the screen. There will be a Q&A session at the end where Mike will have the opportunity to answer some of your questions. And we'll also be sending a recording of the session later to you today. That message will also have a survey, and we'd love to hear your feedback about this session. So with that, I'm going to go ahead and pass you over to Mike.
Hi, everyone. Thank you for tuning in today. It's fun to have the opportunity to share with you some of the knowledge that we have about lab-grown diamonds and hopefully address some of the issues or concerns that you have as you go about your daily work. There we go. So, as Kelly mentioned, I'm going to talk about laboratory-grown diamonds, and I'll touch on some of the identification methods, but also one of my goals is just give you information about how they're grown and what they are. And I always like to start a presentation off with some nice pictures of faceted diamonds. So you have some here down the side, very pretty diamonds. What you may not realize is that they're all laboratory grown, but they're not all grown exactly the same way. Now I've shown you what the crystals from what they were originally grown look like. And you see the top three are very different from the bottom three because there are two major methods by which diamonds are grown in a laboratory. One of them is called high pressure, high temperature growth, and the other is chemical vapor deposition growth. So these top ones are HPHT, or high pressure, high temperature. The bottom ones are CVD, or chemical vapor deposition. So you see the starting crystals look very different, and that's a product of how they're grown. And it also has something to do with their identification, as we'll see going forward. So let's start out with a little bit of the basics. The question is, what is diamond? Well, diamond's a very simple mineral. It's a mineral made purely of carbon atoms. There are a few other little impurities to substitute in, but for the most part, it's simply carbon atoms. But not just atoms all thrown together, they're arranged in a very particular way. On the right here, you can see each carbon atom is bonded to 4 other carbon atoms in a tetrahedral arrangement. This arrangement is very important, as you'll see on the next slide. This occurs naturally, of course, and we all value our mined diamonds, but it can also be grown in a laboratory. And that's why you're tuning in today, is to hear more about that. The structure of diamond gives it some very unique properties that I'll also mention. So diamond's not the only material, only mineral even, made purely of carbon. On the left here, you see graphite, and we all know graphite from the lead in our pencils. And it's a very different material than diamond, much softer, among the softest minerals, whereas diamond's among the hardest. And that difference is not in the fact that carbon atoms, as both minerals are made up purely of carbon atoms, but in the structure. On the left, you see graphite's made of these sort of hexagonal rings in layers that are loosely bonded to each other, whereas diamond has this nice tetrahedral structure and framework that makes it more robust. So the structure itself gives rise to some really cool properties for diamond. First, as I mentioned, it's the highest hardness. It ranks as a 10 on Mohs scale of hardness, making it the hardest natural material. It has the highest thermal conductivity of any other material. It's 5 times a better conductor than copper. It has the highest molar density of any terrestrial material. It sounds kind of convoluted, but what that basically means is the atoms are packed so closely together, more so than any other material on Earth, that you'd have to go to a neutron star to find atoms that are more closely packed together. And finally, one of the more interesting properties is it has the highest sound propagation velocity, meaning that if I could talk to you through a diamond, you would hear me 50 times faster than you hear me talking to you through the air. It's a pretty cool thing and it has some important technological applications. So if you tuned in last week, you heard Dr. Smith talk about natural diamonds. And he told you that most natural diamonds occur at about 150 to 200 kilometers down in the Earth's surface at the base of these thick bits of continent called cratons. They're brought to the surface quite rapidly and violently by magmas called kimberlites, so that they end up at the surface where we ultimately find them. It's how they actually get preserved. One of the more exciting things he talked to you about were recent discoveries have shown that below 600 kilometers in the Earth's mantle, a lot of the very large type 2 diamonds that we really truly prize and value in the industry, they seem to occur much deeper in the Earth. So he talked about all that. What I'm going to talk to you about is what goes on in these little buildings up here on the Earth's surface. And that's where diamonds are grown in laboratories. So before we start, there are some terms that you've probably heard, and I want to just give a little bit of clarification to them. First, natural. In the context of our discussions, natural diamonds are diamonds that grew in the earth and were mined. We're not talking about post-growth treatments or anything like that, but simply diamonds that originated in the earth. These other terms like lab-grown, man-made, synthetic, and even cultured are terms that you hear a lot in the industry, and they're referring to lab-grown diamonds. Things like lab-grown, man-made, and synthetic are terms that are acceptable to use to refer to lab-grown diamonds. Something like cultured, on the other hand, is a bit misleading, and the FTC really strongly discourages its use amongst diamonds. But finally, don't confuse all of those terms with simulant. Everything else listed up here is a diamond. It has carbon atoms arranged in a tetrahedral structure, but a simulant is not diamond. Even though it sounds something like synthetic, it is not in any way the same. A simulant is another material that is made to resemble the appearance of diamond, used as a substitute. So now that we've gotten that out of the way, in the last few years, the lab-grown diamond industry has sort of cranked up, and technological advances have really made them more prominent. People are really wondering what that means for the diamond industry. A lot of these headlines we kind of threw in here for fun. Will we finally say "I do" to lab-grown diamonds? Will lab-grown diamonds save or sink the diamond industry? Is that rock for real? What is a diamond? Is this perhaps the new diamond age? So there's a lot of concern, a lot of emphasis, a lot of curiosity in the world about lab-grown diamonds. As I mentioned in the opening slide, lab-grown and natural diamonds are made of the exact same structure. A diamond is a diamond, whether it's grown in the earth or it's grown in a laboratory, and it has the same chemical and physical properties. But in the jewelry industry, we have a need to understand the difference and be able to identify and separate lab-grown diamonds from natural ones. There are two growth techniques that are used for lab-grown diamonds. The high pressure, high temperature, or HPHT technique, which tries to simulate conditions in the earth with high pressures and high temperatures. And the chemical vapor deposition, which we draw here is sort of a fancy looking little microwave, because it uses certain types of microwaves to grow diamond in ways that you wouldn't necessarily expect diamond to be able to grow. Diamonds have been grown in a laboratory since the mid 1900s. So it's not a new thing, but only in the last several years have they become prominent in the jewelry industry, particularly colorless ones. Sorry to geek out a little with a lot of science, but this is important for understanding what we're talking about. This diagram on the left is a PT diagram, meaning pressure is plotted on the vertical axis going upward and temperature on the horizontal axis increasing to the right. The areas that are white is where diamond is stable, meaning if you have carbon, you will crystallize diamond. And in the red is where graphite is stable. All these other little fields that are shaded show you where diamond grows in reality. This gray oval is where most natural diamond grows at about 5 to 6 gigapascals or GPa and about 1,000 degrees C. This catalytic HPHT synthesis region, this is where high pressure, high temperature diamonds are grown in the current industry. And this area down here in the graphite stability field, called metastable CVD diamond is where CVD diamond tends to be grown. And you're asking yourself, well, that's not even in the diamond field. And we'll talk about that when we get to CVD diamonds. Right now, I'm going to start by talking about HPHT growth, which is this sort of teal colored field. On the right, you see a couple of diagrams of crystals. It's important to understand that different growth regimes have different crystal shapes. Natural diamonds tend to grow as octahedra with 8 different growth directions, whereas HPHT lab-grown diamonds tend to grow as cube octahedron, meaning they have a mixture of these 8 growth directions from the octahedron, from similar to natural, but also the 6 directions of cubic growth. Therefore, giving you 14 directions of growth. This different shape has a big impact on how we look to identify things. So HPHT grown diamonds are grown under very high pressure. Here you see some anvils, 6 different anvils pressing on the sides of a cube, and then a high pressure cell in the middle. This is where the diamond grows. And then I'll show you in a subsequent slide what this little cell looks like. But on the right, this is a factory that grows HPHT, lab-grown diamond. And each one of these green metal devices is one of these presses. This factory is just full of them. It kind of gives you an idea of the scale of how many diamonds are being grown and how many presses are being employed in the industry. When I talk about high pressure, what does that mean? So 5 to 6 GPa, which is about where natural diamonds grow, as well as about where HPHT diamonds are grown, is roughly the equivalent of about 80 elephants all standing on your big toe on a pinpoint. And so it seems silly, but that's a lot of pressure. And it's a lot of pressure because it's simulating nearly 200 kilometers deep in the earth. So this high pressure cell that's in the center of these presses, these large anvils are pressing in, is the most important part to growing HPHT diamond. It consists of a carbon source, which is this black area. It's usually powdered graphite, very pure powdered graphite. A middle section, which is a metal solvent catalyst. It's usually made of iron, nickel, cobalt, and this really facilitates the growth. And then at the bottom is a seed crystal. And this is a very important part of lab-grown diamond growth, is that in order to grow single crystal diamond, you need to start with single crystal diamond. So you need a piece of diamond at the bottom in order to tell the newly growing diamond exactly what structure to grow in, so to mimic that tetrahedrally-bonded carbon structure. This entire thing is under very high temperatures of 13 to 1600 C, as well as very high pressures, as I mentioned, 5 to 6 GPa. What makes this whole process work, though, is the temperature at the top is hotter than the temperature at the bottom, just by a few tens of degrees. But what that does is it introduces a temperature gradient, whereby the carbon atoms, when they're heated, they dissolve into the metal catalyst. And much like somebody who lives in a hot climate who wants to move to a cold climate, they migrate through the solvent catalyst down, and then they encounter the seed crystal at the bottom. They say, okay, I see more carbon atoms just like me, and they're bonded in a tetrahedral arrangement. I'm going to bond that way too. And they slowly migrate down, and a diamond crystal grows up from the seed. But this gradient in temperature is critical for getting the carbon atoms to migrate downward. This whole process can take from days to weeks, depending on how big of a diamond you want to grow. Here are some examples of some big lab-grown HPHT diamonds. On the left is a 4-carat vivid orange yellow diamond. The middle is a fancy deep blue 10-carat faceted stone. On the right is a 10-carat colorless stone of VS clarity range. So 6, 7, 8 years ago, we would have told you that if you see a diamond that's over a couple carats faceted, there's no danger it can be lab grown, because they just can't grow them that big. I think this shows that in the last several years, technology has improved to the point that any size diamond has the potential to be a lab grown diamond. Sort of interestingly as well, this diagram, which increases from year 2007 to 2016 on the horizontal axis, it's showing the percentage of different colored HPHT lab-grown diamonds. Notice that early on, and this is the case since they've been introduced, orange and yellow colors dominated, but technological advancements have allowed growers to remove nitrogen impurities, and nitrogen is very common in the atmosphere, so it's very easily incorporated. Been able to remove that nitrogen, which causes the yellow and orange color, to the point that now there are many more colorless HPHT diamonds that are being produced. And today, that is probably the most common thing that's being grown by this method. Not only that, technology has improved to the point that it used to be that they could only grow a single lab-grown diamond in each one of those presses that I showed you. Now they can grow many all at the same time. Each of these stones is multiple carats in size, and they're all grown in the same press at the same time over the same time period. So this is an important advancement. It allows a lot more diamond to be grown. A couple of years ago, we were shown this crystal from a company called New Diamond Technology in Russia. To my knowledge, it's still the largest one that we have seen. It's 103.5 carats. It's not a lot to look at, and it is yellow, mind you, but this is where the advancement and growth has come by this method. This was grown in 2 weeks in late 2018, but it's 103 carats, which is just absolutely amazing. I wouldn't be surprised if the same crystal can be grown larger today and even closer to being colorless. But I wanted to give you a perspective on the largest that we've seen. Contrast that with what's really of concern in the diamond industry right now, and that is very, very small lab-grown diamonds by the HPHT technique. You see a bunch here on the lower left. Each one of these little crystals is 5 to 6 points, sometimes even less, 2 to 3 points in size. Individual HPHT lab-grown crystals. They're actually grown in these green presses that I showed you the video of earlier, and they can grow tens of thousands of carats of these things each month. It's pretty amazing. Most of this growth goes on in China, but it is done in other parts of the world as well. Each of those little crystals looks like this. It starts out with an industrial quality seed, which is even smaller. Notice the scale bar. This is about half of a millimeter. On that, they grow a single colorless HPHT melee-sized diamond. On the right, you see the faceted versions of these. They cut off the seed crystal and facet the stone. This pile of faceted melee range anywhere from half a point up to 2 points in general, and that's widely available from China and other parts of the world. And it's aroused a lot of concern in the industry for melee mixing between natural and lab grown. I'll make a comment in a slide or two about that later on in the talk. So how do you identify HPHT lab grown diamonds? Well, large or small, the best method is if you have inclusions. Much like natural diamonds will incorporate minerals that they grow around, then likewise, a lab-grown diamond will incorporate the material in which it's growing. And I told you these grow in that molten metallic flux made of iron, nickel, and cobalt. And you see the inclusions that get trapped in HPHT grown diamonds are these metallic, very dark looking inclusions. They're usually a blobby, irregular, or rod shaped, but they're all metallic and reflective, and they look very different than natural inclusions. If you see these, you can be fairly certain that you have an HPHT grown diamond. Here's another slide, just another slide for contrast. On the right, you see some natural diamond inclusions, garnets, olivines, clinopyroxenes, some sulfides. On the left, you see these metallic flux inclusions in HPHT lab-grown diamonds. They don't really look anything alike. The only one that has some comparison would be the sulfide mineral that Dr. Smith talked about last week a little bit, and some of these deep type 2A diamonds in the earth. But these inclusions tend to expand and cause fractures that graphitize and are filled with dark material in natural diamonds, and they tend not to do that in lab-grown diamonds. So even if you see a metallic-looking inclusion, it's almost always going to have one of these dark halo fractures around it if it's in a natural diamond. So not all diamonds have inclusions in them. We know that, both natural and lab-grown. So we need more than just that. And this comes back to the morphology. Remember, I showed you the octahedron and the cube octahedron. Well, here are some natural diamonds that most of which grow either as octahedra, like this one, or over time in the earth, they partially dissolve, called resorption, and they become dodecahedra or more rounded shapes. But there are all some variation, excluding some of these very deep type 2 diamonds, which are often very irregular, like the one in the upper right. But what you do notice is none of the natural diamonds have this nice, consistent cube octahedral shape that you see from the stones on the left, all of which are high pressure, high temperature grown, lab grown diamonds. You have flat cube faces, angular octahedral faces mixed together in all of the crystals. Well, you're probably not going to be fortunate enough to see too many lab grown crystals. The stones are usually already faceted. So, what does this help us? It tells us that the external shape of the crystal is reflected in the internal growth of the crystal. And so on the left here, you have a cube octahedral schematic. If we slice it vertically, we can see that from the seed crystal, we have cube faces growing up, octahedral faces growing at an angle, and faces in between. You have this mixture of different growth sectors or three-dimensional regions that have a common crystallographic plane. Well, if you imagine that we facet this stone. So say we cut the table along this line called B to B prime. So we've got a flat surface here. It's cross-cutting these different growth sectors. If we go over here and we look at the cross section on the far right, we have a cube sector in the middle making a square shape. We have the large octahedral sectors beside it and the ones in between, these 101 labeled sectors. The square in the middle and the arms coming off, the intermediate sectors form a cross shape. And this is very distinctive in diamond. And it's important because different impurities like nitrogen and boron are taken up differently in each different growth sector. And so you get a pattern when you look at the fluorescence. These images are deep UV fluorescence, meaning very high energy ultraviolet light. Not the kind that you hand shine with a handheld lamp, mind you, but more something like a diamond view instrument. They give you very nice detail. You can see on the right square cube sectors, large octahedral sectors, and the ones in between fluoresce very differently, creating a square or a cross shape in all of these images. This is pretty much diagnostic of HPHT lab-grown diamonds. And it's very important. Not only that, the color of the growth sectors tells you something. When you see sort of green or bluish green fluorescence, then you know that you're probably dealing with a lab-grown diamond. And if you turn the UV source off and the diamond's still glowing, still emitting light, called phosphorescence, it's another very, very strong sign you're dealing with an HPHT lab-grown diamond. Very, 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 very few natural diamonds have these properties. Here's some examples. These are some colorless HPHT lab-grown diamonds. Hopefully you can see the pattern, that the less fluorescent square and arms in each one. If you can't, they're drawn in for you. The cube and the octahedral growth sectors to make a cube octahedral growth form. And then the strong phosphorescence seen in the lower left-hand corner. All of these are good indicators that you're dealing with a lab-grown diamond. So how does that compare to natural diamonds? Well, here's some examples. At the top are some more of those HPHT lab-grown stones. Most natural diamonds that show good patterns show squares, and this is what you get when you cross-cut an octahedron. Remember, an octahedron has 8 sides, and its cross-section is a square. As they grow larger and larger, you get squares inside of squares inside of squares, sort of square tree rings, so to speak, reflecting natural growth zones rather than these cube and octahedral mixtures. So they're very distinctly different in this deep UV fluorescence. Well, not everyone has access to a deep UV device. We understand that. And there's some cool things that you can actually do with just a handheld UV lamp, like the one in the upper right here, that does long wave UV and short wave UV excitation. What we've discovered over the years looking is that The vast majority, and over the last decade, 98% of the colorless HPHT lab-grown diamonds that we've seen do not fluoresce to long-wave UV, but most of them do fluoresce to short-wave UV. That means that if you see a short-wave UV reaction that's stronger than a long-wave UV reaction, you're probably dealing with a lab-grown diamond. Fortunately, this is going to hold true for all types of lab-grown diamonds, and it is the exact opposite of natural diamond. Natural diamond tends to fluoresce. If it fluoresces at all, it fluoresces to long-wave UV and very little to short-wave. So the takeaway point here is if the short-wave UV reaction is stronger than long-wave, you should be very worried that you might have a lab-grown diamond. But we mentioned phosphorescence as well, and it shows up to the shortwave component of these handheld lamps. If you put the shortwave UV light on your diamond and you turn it off and the diamond still glows, it's phosphorescing. This is a very good sign that you're dealing with a lab-grown diamond. This reaction is called by trace amounts of boron impurities in the diamond that are incorporated during growth in the laboratory. Only a very tiny, less than 1% of natural diamonds will have these types of features, and when they do, they're not as intense as they are in lab-grown diamonds, so you're very unlikely to ever see that in a natural diamond. Another trick you can use with a microscope is something called cross-polarized filters. It's investigating a property called birefringence, or the amount of strain in the diamond. If you take two polarizing filters, similar to what you get in polarizing sunglasses, and if you hold them on top of each other and you rotate one of them, at some point, looking through them, it becomes black because no light's allowed to pass. Because polarizers have different orientations. And when you perfectly cross those orientations, light cannot come straight through. So diamond is an isotropic mineral. This means that effectively that if you shine light through it in different directions, the light passes through at the same speed in all those directions. So if you put an absolutely perfect pure diamond underneath in between two cross polarizing plates, you won't see any pattern. It'll be dark as you look through. But natural diamonds, because they reside deep in the earth, they're under lots of pressure and temperature. They get strained, meaning their atoms are twisted and moved a little bit. And they're not perfectly isotropic anymore. So as a result, when you put a natural diamond between cross-polarizing lights, some of the light gets bent a little bit and is able to pass through the upper polarizer. So you get patterns like those seen on the left two images. Usually either linear or crisscrossing with different colors ranging from gray or blue to pink or yellow, depending on how much the diamond has been strained. The nice thing is HPHT lab-grown diamonds do not experience any of that strain. And so when you put them under cross polars, you see no pattern, like the samples on the right here. See, there's a very distinct difference between the two. This lack of strain pattern is a strong indicator of lab-grown HPHT diamonds. Now I'm going to talk about CVDs in a bit, and unfortunately this doesn't apply because the CVD growth process will produce patterns similar to natural. But if you see no strain pattern, then you can be fairly sure you're dealing with a lab-grown HPHT grown diamond. All right, speaking of CVD, let's go into CVD a little bit now. So the same diagram is here, but now we're talking about this field down on the bottom, this metastable CVD diamond. And we call it metastable because it's in the graphite field, meaning carbon should not be able to crystallize into diamond there. But it does, and it stays diamond, much the same way that the ring on your finger with a diamond in it is a diamond, and it's not graphite, even though we're technically in the graphite stability field at the Earth's surface. So the trick with this is the same as the ring on your finger. If you can make diamond, there's not enough energy to break that diamond apart and turn it into graphite. So the trick is getting the diamond to grow at all. And they do that with a very specialized approach that I'll illustrate in the next coming slide. All right, so this slide shows you what a CVD reactor looks like. On the left here, it will fit on your standard size table. It's not a very big device, but the control boxes that are required to run this device can take up an entire room sometimes. Notice there's a little window here. Inside that window is where you can see the diamond growing. There are lots of little substrates or seed crystals of diamond on which the CVD diamond grows. Above that is a very hot plasma. And above that, the gases are put into the reactor. The plasma causes the atoms to break apart, the molecules to break into atoms and smaller molecules. Thus, we have a gas phase chemical reaction. The gases used are methane and hydrogen. And I'll explain to you on the next slide why methane and hydrogen are important. This whole thing is kept under vacuum. So no high pressures here, no elephant sitting on your toe. Now we're actually below atmospheric pressure. And we're at temperatures of up to about 1,000 degrees C. Same time period, depending on how much you want to grow, days to weeks. So how does all this happen, and why is this plasma important? For that, we have to go to the next slide here, which is, there we go. So this video hopefully is showing for you guys. These are all atoms. The red atoms are carbon atoms. The white atoms are hydrogen atoms. So I know it seems a bit overwhelming, but bear with me. All the red atoms in the bottom are the diamond, the seed crystal of diamond. If you want to grow diamond, you have to start with diamond. All the outer surface of the diamond carbon bonds, where the carbon doesn't have another carbon to bond to, is bonded to hydrogen, because there's hydrogen everywhere in the atmosphere. Up here is the plasma. The plasma has different white hydrogen atoms floating around. It also has different carbon base. See, here's a CH3, and there's CHs and CH2s, all that are broken up from the methane, which starts as CH4, but the plasma causes it to split into other molecules. So the single hydrogens are cleaners, they're sweepers. They come down and they pluck single hydrogens off the surface. You can see them periodically. They'll grab a hydrogen and they're happier with two hydrogens together. When they do that, they open up a carbon slot. And that carbon slot then allows another carbon atom to come down and bond. And it bonds in the same tetrahedral structure as the ones underneath it. And we slowly grow diamond, one atom at a time, upwards. By doing this, we can make diamond grow in a place that diamond wouldn't necessarily grow. And once we create these bonds, they don't break apart anymore. So we can slowly, atom by atom, layer by layer, grow diamond. So hopefully that clarifies that part a little bit. All right. So when you grow a CVD diamond, it's not so pretty when it comes out. It looks more like the one on the left here. The diamond is the brown bit in the middle. All around the outside is a whole bunch of polycrystalline diamond. This polycrystalline diamond is the material that grows off of the seed crystal. Underneath this is the seed crystal itself. So there's a whole series of steps that have to be done as you deal with CVD diamond. First, you grow it and you get this. Then you need to laser cut the substrate or the seed crystal off. The yellow part is the seed, the white is the newly grown CVD diamond. We cut right through here. Then we have to get rid of the outside, so we actually laser cut a shape depending on what we want to facet. In this case, if I want to facet a round brilliant, I cut a cylinder out of the middle, and then I can facet my round brilliant from yours. All right, so if you want to cut different shapes, you cut different shapes out of the middle. If you want a rectangular shape, you cut a cube. If you wanted to cut more than one round diamonds out of the same piece, you might cut a cube and then angle the growth or the cut direction of the diamond. So the takeaway point of this is that unlike HPHT lab-grown diamonds, where you just get the crystal and facet it, you have to do a whole lot more with CVD. There's several steps. Not only that, you probably noticed that that diamond was brown, and you're like, most lab-grown diamonds are not brown. Well, it's much easier to grow CVD diamond brown, and much faster, actually. And they discovered several years ago that you can take this diamond and you can put it in a device very similar to that which HPHT diamond has grown and treat it in a way that decolorizes it. Natural diamond can be decolorized the same way. It goes from brown to near colorless, and you can do this in a matter of minutes. So it's much more efficient to grow as brown and HPHT treat to colorless. In fact, over a long period of time, over a decade, we looked at all the CVD diamonds we had seen, and nearly 3/4 of them have been decolorized by this method. So it's very, very common. What this does introduce, though, are two distinctly different sets of properties for identification. When you have the as-grown CVD and you have the treated CVD, it changes some of the fluorescence and other properties. So we have to look at each one of those separately. So much like I mentioned with the HPHT diamonds, a few 7, 8 years ago, we would have told you if your diamond's bigger than 2 carats, it can't be lab grown. Even more so with CVD because it's a much more difficult growth process. But here are some examples to show that this day and age that doesn't apply at all. And notice the colors and the clarities on some of these; they're quite spectacular. 5 carats, 6 carats, D equivalent, so colorless, very slightly included clarity range, all the way up to the largest that we know about right now in faceted CVD, which is 9/9 carats. So there's some very large, some very nice CVD diamond out there. I wanted to give you a bit of a timeline because I talk about how things change, and I thought this was kind of fun going from about 2003 up to about 2018. On the vertical axis is the carat weight, but you can just look at the chart itself. The initial diamonds up to about 2008, CVD stones we saw never really got much larger than a carat faceted. They were brown. Then somewhere between 2008, 2010, they learned how to decolorize them or occasionally grow them colorless very, very slowly. But then we noticed that 2013, the size increased to 2 carats, and then 2015, 2016, it really started to take off. The technology advanced to the point that we really started to see big stones, 3 carats, 5 carats. And then in May of 2018, we got reports of this 9 carat faceted stone. We've also started seeing treated color CVDs getting very nice, intense pinkish orange colors. So not just colorless, they can also be colored. This gives you a bit of a time frame and how much the technology has really taken off in the last 5 years. Pretty remarkable. Well, much like the other lab-grown diamonds, CVDs also occur as melee. This is just an example from a parcel that was sent into a GIA laboratory for examination. 30 carats, all consisting of 6-point stones. Of this 546 melee, 542 of them were CVD grown. Only 4 were natural. And this is highly unusual, but it's to show you that the CVD melee is out there. The HPHT melee is far more common, but CVD is sometimes cut into melee as well, so you can't discount that idea. Looking at some identification features, I talked about how important inclusions were to the other types of lab-grown diamond. Well, in CVD, they're not quite as valuable because most CVDs are very high clarity. The chart on the right shows you that this is simply percentage of CVD diamonds, and you see the vast majority are in the VS, VVS range of clarity. They go all the way up to internally flawless. If they do have inclusions, they tend to have these little black, wispy, non-diamond carbon inclusions, sort of as you see in the lower left. Some natural diamonds can have these types of features. If you do see these, I would say be very wary. And actually, a few weeks ago in the laboratory, I saw a CVD diamond that had something that looked very, very similar to this. And so keep your eye out, but they're not always there. So it's not nearly as strong of an identification tool as it is in the HPHT grown stone. So we talked about the cuboctahedral growth for the HPHT diamonds. It's a vertical cube growth for CVDs, but it has an effect on the growth shape because while most of the growth is going upward, at the same time, there's a little tiny bit of lateral growth on a microscopic scale. What it does is it creates sort of a pseudo mini micro stair step structure. Rises or steps and little intermediate growth sectors, which we refer to as striations because they're so tiny, they just look like lines when they incorporate different impurities in the fluorescence. What does that mean? Well, let's look. Well, I apologize. I want to talk about growth first. It'll be on the next slide, the striations. So it's hard to grow CVD diamond for a very long period of time without something going wrong. So initially, they would grow as thick as they could, and they would develop these striations, which are at angles to the substrate. But we didn't get large CVD diamonds because it's very hard to grow thick enough to get a large diamond cut out. So what growers started doing is interrupted or layered growth, where they'll grow a little bit, they take it out, they polish it, then they put it back in, they grow a little more, they polish it, then they grow a little more. You still get the striations in the layers from the growth, but you also get growth interruptions. And each time you stop, some impurities are taken up in the structure and they fluoresce differently. So let's see what I'm talking about. So these are as grown CVD diamonds. They fluoresce either orange or red typically. And you see all these little subtle parallel lines. Some of them look angled, but it's mainly due to the faceting, the way the faceting is showing here. But these repeating lines are striation. And these are unique features to CVD diamond. Deep UV fluorescence here we're looking at again. On the right, you see the striations are in each layer, but you see very distinct layers, sort of like a layer cake. Each one of these growth interruptions is where they started and stopped the growth so that they could grow thicker and thicker and thicker. So it kind of gives you an idea that the fluorescence really gives away that these are CVD diamonds. You don't see these textures in natural diamonds. Those were as grown. These are the ones that were decolorized by treatment. And you notice we still get the very nice striations. We just get a very different background color. Here we have different defects or imperfections in the diamond structure that's causing the fluorescence to be a different color. But the structure, the striations, and the growth interruptions are still the same, which is pretty fantastic when you're trying to identify these things. That part at least doesn't change with treatment. Much like HPHT, you can do a little bit with your handheld UV lamp as well. Even more so than HPHT, very few to any, basically no CVD diamonds will fluoresce to long wave UV, whereas most natural diamonds do. That means that if you see a short wave reaction stronger than a long wave reaction, again, it's likely lab grown. Doesn't tell you CVD versus HPHT, but it's a good indicator that you're dealing with a lab grown. And I'm assuming that most of you probably don't care whether you're dealing with a CVD or an HPHT, just that you're dealing with a lab grown diamond versus a natural one. So having this difference in reaction is critical with a simple handheld lamp. Now it starts to get a little tricky with phosphorescence because as grown CVD diamonds don't always phosphoresce. But usually those that have been decolorized, which as I told you earlier is nearly 3/4 of the stones we've seen, will have a greenish phosphorescence to shortwave UV. And so when you see this phosphorescence to shortwave UV, then you can really be concerned you might have a lab-grown diamond. All right, and then something on advanced instrumentation. There's an interesting impurity that goes into CVD lab-grown diamonds. And this is that not just nitrogen and boron is an impurity, but silicon, which is very, very, very rare for natural diamonds, but it's very common in CVD grown diamonds. And that's because this little window in the reactor and some other quartz containing components within the reactor get etched by the very hot plasma, and the silicon atoms get brought into the plasma, and then they can drop in the vacant spots in the diamond structure that's growing and be incorporated within the diamond. Using a very sensitive technique called photoluminescence with lasers, we can measure light coming from these silicon atoms as these very distinct sharp peaks at 736.6 and zero point 0.9 nanometer positions. This tells us unequivocally that silicon is present in the diamond lattice. And so when you see silicon, you assume CVD diamond. So it's a very, very good indicator. All right, so quickly I want to touch on some developments. I know I'm running a little long here, I apologize, but if you've heard of Lightbox, Lightbox is a new line of CVD synthetic diamonds that are being marketed by a company called Element 6, which is owned by De Beers. I'm pretty sure they sell them as blue, colorless, and pink. But they're all as grown CVD diamonds, and we saw a couple samples when they were launched, and they're very nice stones in the near colorless range, very good cuts, and very high clarities as well. Light box diamonds have a very distinct logo etched just below the diamond surface that you can see pretty distinctly with a microscope. But probably the most important factor is that when De Beers entered this industry, they really did some interesting things in pricing. They priced 1 carat stones at $800, and that is far below what most lab grown diamonds, in particular CVD lab grown diamonds, had been priced at. Previously, they were done as a percentage of the natural diamond price, and so this really sort of shook up the lab grown diamond industry in terms of pricing a bit, and has really led to some changes there. I also wanted to talk to you about some things we've seen in the laboratory. These are not common, but they do occur, where natural diamond is used as the seed crystal, and on it is CVD is grown. In this instance, the pavilion of this round of brilliant is a natural diamond, and the crown is CVD. In this case, the CVD was grown to add weight, and it adds nearly 30% of the weight of the stone in lab-grown diamond. So these are sort of mixtures or hybrids or whatever you want to call them. We don't have a formal term for them, but they're mixtures of natural diamond with lab-grown CVD diamond on top. You can't do this with HPHT grown diamond as well, because the seed is always removed. But if you use the natural diamond on which to grow the CVD, it's a much more viable thing. Deep UV fluorescence shows us the blue fluorescence that's typical of natural diamond, and then sort of pink that comes from as grown CVD diamond. Along those same lines, we've seen stones where extremely thin layers, like this 80 micron layer, which is about the thickness of a human hair, of boron doped CVD was grown on a natural diamond. The boron causes blue color in the diamond, and it gave this diamond, just this tiny little bit on top, gave this diamond enough to be called fancy blue by color grading systems. It's less than 0.08 millimeters thick. It's absolutely amazing. But the deep UV imaging shows us the pavilion, the natural part, fluoresces blue, and the crown fluoresces green, which is very, very different. And so it helps us separate it. But I just want to make you aware that these sort of hybrid mixed natural and lab grown diamonds are actually occasionally produced. I don't know how prominently. We've only seen a handful of them, but they certainly are out there. I should have mentioned here that on the lower left, you see some arrows. This is not really visible in the microscope. There is a tiny feature there after you know it's there that you might recognize, but I saw this stone. I could not see it. Most of the gemologists could not see it either without being told that it was there. So it's something that you have to be very, very aware of. If you used a tester on the crown versus on the pavilion of one of these stones, you probably get different testing results. So it's a good thing to keep in mind. All right, so you may know the diamond pipeline from exploration to mining, cutting, grading, and retail. Now, with lab-grown diamonds being more prominent, we've got a parallel structure where we have lab development and factory growth to sort of parallel the natural diamond industry, but everything gets funneled into the same cutting, grading, and retail sections. And that makes it critically important that the grading and gem labs can separate them, but also that you are able to screen diamonds as well. And why is that important? Because I talked to you so much about melee earlier, and this ring has 70 melee diamonds in it. Well, one of them, that one, is lab grown, HPHT lab grown diamond. The rest are natural diamond. Very, very difficult to know that without having the types of equipment that would allow you to do that. Maybe the ability to test the individual stones, or in the case of deep UV fluorescence over here, you can see that the greenish blue fluorescence and the strong phosphorescence give it away. But you have to know to do this, and you have to have the ability to test. And most people don't have deep UV available to them. As a result, there have been a lot of diamond screening devices that have entered the market in the last many years. These are just a few of those available. I just gathered some different snapshots. but there's a ton of different ones and they use different technologies. And I'm going to just briefly touch over the last couple of slides on those technologies. There are 6 main technologies that are in play when you look at all of these types of instruments. And they involve UV transparency, or the ability to pass UV light through a stone. UV visible absorption, which is the same thing, just using a spectrometer to measure a spectrum. Infrared absorption spectroscopy, which involves passing infrared light through. Phosphorescence imaging, which is measuring that phosphorescent property by taking images of stones once you turn the UV light off. Using spectra to measure the decay, or how long that phosphorescence takes to go away. And then finally, looking at fluorescence spectroscopy, or collecting spectra from stones while the UV light is on to measure the fluorescence produced by the defects that are present. So these techniques are incorporated in various different machines, but I'm going to comment just on 4 of them and talk about some of the advantages and disadvantages, because these are the most prominent ones. UV transparency is predicated on the amount of nitrogen impurity that's in a diamond. So colorless lab-grown diamonds are type 2, meaning they have no measurable nitrogen in them. That's why they're colorless. So UV light should pass through them. If the diamond has nitrogen in a natural one, it tends to absorb the UV and it does not pass through. This is the easiest method to do, and it costs the least, and it's been around in screening devices for the longest time. Infrared absorption spectroscopy, collecting an infrared spectrum. This is the fundamental way that diamond type 1, type 2, or nitrogen and boron impurities are measured. So obviously, if you're trying to separate type 1 and type 2 diamonds, this is the fundamental way to go. Phosphorescence imaging is the most common amongst devices because it's the easiest to build, not necessarily easy to do, but the easiest to build as a device, because you're just taking images. And it's very visual. People like visual things. And then finally, fluorescence spectroscopy. And this is important because you're looking at defects that come from natural features. You're not necessarily looking for what is lab grown about the stone, but what makes it natural. So each of these has some disadvantages, and you should be aware of these. I'm not saying one's necessarily better than the other, but you should be aware of their limitations. UV transparency can miss synthetic diamonds or lab-grown diamonds, and it can pass simulants because, for one, it's assuming that you're using diamond, and there's some lab-grown diamonds that will absorb UV light like natural diamonds do. It also has a very high false referral rate. Infrared absorption spectroscopy, if you have stones with poor clarity, you can't get the light through. That's a big problem. And the analysis is relatively slow. It takes longer to collect a spectrum. Phosphorescence imaging, it's nice, it's visual, but unfortunately, notice I told you that some of the treated CVDs phosphoresce, some don't. Most of the as-grown CVDs do not phosphoresce very well. So if there's no phosphorescence, this technique assumes that you're dealing with a natural diamond. Likewise, it assumes that you're putting diamond in, so it can pass simulants as well. Something I didn't talk a lot about, but there's also a way to take lab-grown diamonds that phosphoresce and do a radiation treatment on them, and you can actually reduce or eliminate their phosphorescence. And if that's employed, a technique that's looking for phosphorescence would be fooled, and it would allow lab-grown diamonds to pass as natural. With fluorescence spectroscopy, which is one of the more robust methods, it does have the problem in that because it's looking for natural features, it may not always see those in every natural diamond, so it may refer a small percentage of natural diamond. So with that being said, I'm not going to comment on the quality of any of the devices, but I wanted to make you aware that there are organizations like the Diamond Producers Association that have done testing on different screening devices. And they make that testing available to you under something called Project Assure. If you go to the Diamond Producers Association website, under Project Assure, you can download the test results for any device they tested, and they did quite a lot. Here I show you just the results for GIA's ID 100, which separates natural and lab-grown diamonds. So if you go down through, you get lots of information about the device. And I apologize, this is a little blurry, but this is just the way it blew up. The key parts are in the test results. The diamond false positive test rate is how many natural diamonds did the device call lab-grown. In our case, it was 0. Then the synthetic diamond false positive rate, how many synthetics did it call natural? We tested as a 0, which is great. And then finally, the simulant false positive rate. How many simulants did it call diamond? And it was 0. So these are the key numbers. If you're going to use a device, you want to make sure that it's not going to call natural, lab grown, or simulants the wrong thing. So I encourage you to go have a look if you're interested in buying a device. There's a lot of good data on here, and it'll give you some very good information about each of those different devices. So with that, I'm gonna to stop here, and I wanted to let you know also that myself and some of my colleagues have authored some very nice articles with a lot of this information and even more in our journal, Gems in Gemology. Those are available at the GIA website for free. You can go and just download them. The two articles that are mainly of interest are about CVD grown diamonds and HPHT grown diamonds from 2016, 2017. So go have a look if you want more information. I think it'd be really useful. But aside from that, hopefully I can answer a couple questions here at the end, and I hope this has been useful information and that you've enjoyed.
Thank you so much, Mike. That was all such fantastic information. We do have a few questions from the audience. I will mention some people were asking about the GIA ID 100. If you go to store.gia.edu, you'll be able to find more information about the device, including the price. And so then let's get right into some of the questions about lab grown diamonds. So first on the list, what is the best way, or I guess, is there even a way to site ID a lab grown diamond?
Site ID is dangerous in most any aspect of identification. If you mean just looking at it without any sort of magnification, it's not something I would recommend ever trying. I don't think there's a reliable method for that. If you have a microscope or even a loop, immediately go and look for inclusions. Those metallic inclusions are very distinctive, and they're quite common amongst HPHT grown diamonds. Uh, if you see them, great, probably lab grown. If you don't see them, you can't really assume anything because CVD don't usually have inclusions, and natural sometimes do not as well. So if you see natural crystals, great, it's natural. You see metallic flux, it's HPHT grown synthetic. You don't see anything, you got to be really careful.
Great. Um, should the seed crystal be natural, or could the seed crystal be a synthetic diamond?
Oh, that's a good question. Typically, the seed crystals are lab grown diamonds because it's nobody really wants to slice up their natural diamonds into plates to grow diamond on. It's much more expensive. There's another reason that lab grown diamonds, and usually HPHT lab grown diamonds are used, is because if you have imperfections in the diamond structure in the seed crystal, those tend to grow into your newly grown lab grown diamond. So you want the purest thing that you can get. And as I showed you from the strain, the HPHT lab grown crystals tend to be the best structure, the purest structure. So they're usually used. That being said, you can grow diamond on diamond. It can be natural, it can be lab grown, CVD or HPHT, synthetic, either way. So you just need diamond, but it's most commonly
Okay,
done on
great.
synthetic diamond.
And just to let everyone know, we are just about out of time, but if anyone who can stick around. We have a few more good questions, so we'll ask, but um, but just want to let everyone know that we will go a little long. We have another question about the seed. You said in the HPHT process that the seed is removed. Does it get used again?
Yes, they have to repolish it and clean it up. But they try and reuse their seeds from both processes actually, because it gets removed from CVD as well. They use lasers to cut them. With HPHT, it's much easier to get the seed off. It's not as adhered as uniformly because we're not talking atom by atom, layer by layer growth. But they reuse in both types of synthetic growth.
Okay. Now, as crystal growth is sped up, does that increase any impurities or dislocations?
Yes, that's why they. Um, well, HPHT growth occurs at a fairly uniform rate. You can't really speed it up. You put it in the reactor and it grows over a certain period of time. The size of your crystal is contingent upon how long you let it grow. With CVD, the rate is very important. It, the slower you go, the fewer impurities that are taken up. With this atom by atom growth, there's a lot of opportunity for other things to get stuck in there. And so, yeah, the slower grow, the better, but it's not cost effective to grow super slow. And they found that if they add a little bit of nitrogen impurity, they can grow faster for CVD, but that's where that brown color comes from. And thus, they need to decolorize them.
Okay. Is there any reason why diamonds can't form an octahedron during HPHT? And do you think that with advancements in technology, that could actually become a reality?
The growth, excuse me, the growth shape has to do with the pressure and temperature conditions, as well as the time over which the crystal is growing. Natural diamonds grow over a long period of time at lower lower temperatures and about the same pressure as HPHT grown synthetics. But in order to grow effectively, they need to increase the temperature in the HPHT growth process so that they can do it in days to weeks and not take a million years. And when you do that, you end up with a mixture of cube and octahedral growth. So no, it's not a viable expectation that that's going to be eliminated.
Okay. What defect causes fluorescence and phosphorescence in laboratory grown diamonds? And can they fluoresce any color besides bluish, yellowish, and greenish?
Yeah, keep in mind that a lot of the images I showed you were deep UV images. Fluorescence is something that I've studied a lot, and you have to be careful because the excitation wavelength that you use, the energy of the UV light, will affect the color of the fluorescence that you see. So the greenish bluish is what we typically see under deep UV. Very common. It's caused by boron that's incorporated in the HPHT grown diamonds. And the defect is a boron related defect that causes both that color and the phosphorescence. There are plenty of defects that cause different colors of fluorescence. The reason you see the change from the sort of pinkish or reddish fluorescence in the as grown CVDs, that defect is called the nitrogen vacancy center that creates the red fluorescence. As you decolorize that diamond by treating it, you change that nitrogen vacancy defect into a defect that consists of two nitrogens and a vacancy. And that defect fluoresces green, which is why you see the change to the blue-green in that instance. So each case is a little bit different. They're all caused by different defects, but it's very quantifiable. Unfortunately, that's another hour to 2 hour long lecture unto itself.
That's great. We'll add that to the list for future knowledge sessions. Okay, so I think, we're about 5 minutes over, so I think this is probably a good time to end it. I know there are a bunch of other questions that we didn't get to, so if you wanted to reach out to us and ask any more questions, feel free to connect with GIA on any of our social media, or go ahead and go to gia.edu and go to contact us and let us know if you had any other questions. We'll also be sending an email to everyone that registered with a link to this presentation in full, and we'll also include a survey there. So again, we'd love to get your feedback. So thank you so much, Dr. Breeding. This was like, such a great session with so much information. So um, thanks for everyone for attending, and don't forget to tune in next week where we'll be joined by Aaron Pahlke to talk about GI's field gemology program and colored stone origin determination. So thanks everyone.
Bye, everyone.
Bye.